So a couple of you do need to make up the quiz. You can do that after class today. Or, I mean, I can have you do it across the hall during class today and watch the recording, but that's DJ and Gail. But I'm just going to get started. Okay. So, chapter 2.1 homework is due today, before tonight. The second chapter 2 homework will be due in a week on Wednesday the 11th. You can request an extension on past due assignments. The easiest thing to do is to do the automatic extension, because for manual extensions, I have to get an email, see the email, and do something about that, and that could take a day. We have the chapter 1 quiz. The chapter 2 quiz will be in a week on Wednesday. Like all quizzes, you get a page of notes that you can use for reference. The chapter 1 and 2 exam will then be on Monday the 16th. So not next week, but the week after Monday will be the exam on chapters 1 and 2. You also get a sheet of notes for reference for that exam. And we will not be having a lab on the 16th because we'll have the exam and then we'll just not have a lab that day. If you need to make up anything, you can make things up then. Question? There's Mondays. In the next time slot, I'm teaching another class. The labs are on just on Mondays. If you look at your schedule, you'll see it's scheduled only for Mondays. So we were discussing acceleration. We talked about linear acceleration, circular acceleration. Remember that in general, acceleration is the change in velocity over the time. And you can rearrange this to be final velocity is initial velocity plus acceleration times time. A common case of constant acceleration is a dropped object. Any falling object has an acceleration of g. 9.80 meters per second squared. So the distance an object will fall will be 1/2 g times time squared. The velocity, the final velocity for a falling object, is a simplified version of that more general equation. Final velocity is initial velocity plus acceleration times time. Well, the initial velocity is 0, the acceleration is g, so the velocity or the speed is just gt. So after 1 second, the distance traveled will be 4.9 meters. Speed will be 9.8 meters per second. After 2 seconds, the distance traveled will be 19.6 meters. The speed will be 19.6 meters per second. After 3 seconds, the distance traveled will be 44.1 meters. The speed will be 29.4 meters per second. And after 4 seconds, it will have fallen 78.4 meters, and the speed will be 39.2 meters per second. Now, it turns out the vertical component of a projectile, a thrown object, or an object that's just sort of affected only by gravity, the vertical component is exactly the same as if it was going with the speed it has vertically straight up and down. You can treat the vertical and horizontal motion independently. Horizontally, it'll travel at a constant speed in a straight line. Vertically, it will have a constant acceleration downwards due to gravity. So a horizontally projected object, if you fire something horizontally at it will fall at the same rate as a dropped object. So if I fired a ball and dropped a ball at the same time, they'll hit the ground at the same time. I don't have a good setup to demonstrate this. I have a little demo thing, but it's really hard to make sure that it works right. Because it's just a 3D printing thing that doesn't work very well. So an object that's thrown horizontally will fall at the same rate that an object that is dropped. So the velocity in the horizontal direction does not affect the velocity and acceleration in the vertical direction. This is generally true. You can treat the horizontal velocity independently from the vertical velocity. Now, if it's projected at upwards at some angle, you'll have a vertical going up and coming down and a horizontal moving sideways at a constant speed. We're not going to go into how you solve that because we're not dealing with going up and going down. We'll just talk about a few specific situations. Much like if you throw something up in the air, when it comes back down, your speed at the same height will be the same. So your speed, if you throw this up, you'll have the same speed, but going down at an angle here. So when you throw a football, the horizontal speed will remain constant. The vertical speed will change. So it'll slow down vertically until it reaches the peak, then it'll speed up vertically going down. And when it's at the same height as it was thrown, it'll be traveling at the same speed vertically as it was thrown, but now down instead of up. So if you have a horizontal cannon on the top of a 12.25 meter wall, and you want to figure out how far your cannonball goes when you fire it at 100 meters per second, well, the first question you have to ask is how much time does it take for the cannonball to hit the ground? And this we can figure out just by how long would it take for a dropped object to fall 12.25 meters? We can ask that question. So our vertical distance is going to be 1/2 g times time squared. So 2 times the vertical distance equals g times time squared equals 2 times the vertical distance over g. So the time is going to be the square root of 2 times the vertical distance over g. So 2 times 12.25 meters over 9.8 meters per second squared is 2.5. And the square root of 2.5 is 1.58. So the time will be 1.58 seconds. Yes.
The 2G compound from the first.
This 2?
Yeah.
I multiply both sides by 2 to get rid of the 1/2. Because I'm dividing by 2 here, so I multiply by 2 to get rid of that 1/2. So it comes from the 1/2 on the other side. And then the distance horizontally will just be the horizontal velocity times the time. So 100 meters per second times 1.58 seconds gives you 158 meters. So this cannonball will travel 158 meters horizontal. So here's another example. A projectile is fired from the top of a 44.1 meter pole at 5 meters per second horizontally. And this is asking you how long does it take to hit the ground, how much time, and how far from the pole is the projectile when it hits the ground. So going through this one, the horizontal distance, we use the same formula. Horizontal distance is 1/2 gt squared. So twice the horizontal distance is gt squared. We divide both sides by g, take the square root of both sides. We get 2 times the vertical distance over g. I said horizontal accidentally, I meant vertical. This is all vertical. 2 times the vertical distance over g, square root. So 2 times 44.1 meters over 9.8 meters per second is 9 seconds. The square root of 9 is 3. So the time is 3 seconds. Horizontal motion is going to be speed horizontally times time. Well, our speed horizontally is 5.9 meters per second. Our time is 3 seconds. The horizontally, it will have traveled 15 meters. I'm not going to have you do all these calculations on a test or a quiz. I have a multiple choice question, which gives you some extra information, so it's pretty straightforward. But here we do have a question here. If you hit a projectile at an angle, it will travel in a parabola and eventually land on the ground, some distance from where you hit it. If you can hit it, if you can fire it at some speed, but vary the angle where you're going to get the maximum range, the furthest, is at 45 degrees, assuming there's no air resistance. Reality has air resistance, so that changes the calculation a little bit, but assuming there's no air resistance, if you have a cannon that you can fire at a constant speed at any angle, the angle that will give you the longest range is 45 degrees. However, there's another factor. It turns out that if you fire it at two angles that add up to 90 degrees, so here like at 30 degrees and 60 degrees, the range will be the same. Basically, this path is shorter, but you'll be traveling fast. So you have less time in the air, but you will have a bigger horizontal component of velocity. This path has more time in the air, but has a smaller horizontal component of velocity. And it turns out, if you do all the math, they work out that if two angles add up to 90 degrees, they'll have the same range. The actual formula for range, which you do not need to know, is speed squared, initial speed squared over g times the sine of twice the angle. And it turns out for the sine of twice the angle, if you have two angles between 0 and 90 degrees that add up to 90 degrees, they'll have the same sine of twice their angle, twice the angle. I will not go into why that's the case, but that is the case, so you could prove it with some trigonometry. So if air resistance is neglected on a level ground, two projectiles that fired at the same speed with complementary angles, they add up to 90 degrees, will travel the same distance horizontally. So here, 30 degrees and 60 degrees. Same is also true for 20 degrees and 70 degrees. And the longest distance is at 45 degrees. Now, with air friction, things change. Basically, it is better to have a lower path that spends less time in the air, because there's less time for air to slow you down and reduce your path. So your best angle is going to be a little bit less than 45 degrees, because your path gets shortened and ends up asymmetrical, not symmetrical anymore. Because air resistance reduces the horizontal velocity, you get a better effect at a slightly lower angle. But the calculations get really complicated really fast when you start including air resistance. But here are some of the considerations you might take into account. And if you do sports, you probably do take these all into account, but you don't think about them with numbers. You just think about them, this is how I do the thing so I get the best result. You internalize the output. But there's factors like the angle of release, what angle you're releasing it, the spin on the ball has an effect because it can cause lift, the size and shape of the ball or projectile. You throw a javelin different from how you throw a baseball. The speed of the wind, the direction of the wind, both of those are going to affect the movement of the object. Things like weather conditions, humidity, rain, snow, etc. The altitude of the field. The higher your altitude, the less air is present, the less air resistance there is. This is part of why Denver has a whole lot of home runs compared to other stadiums, because they have less air. So there's less air resistance, so balls travel further. There are also some additional effects, but training in high altitude can also have good effects because it makes your body a little more efficient at pulling oxygen out of what you breathe because there's less oxygen available. And then when you go to lower altitudes where there's more oxygen available, suddenly you have tons of oxygen to use. So that's the thing. But it is a distinct factor in Denver's baseball stadium that they have like further hits because there's less air resistance. Initial horizontal velocity, in order to make it out of the park before gravity brings it down, a baseball has to leave the ball bat at a high velocity. So here is a quick problem. If I fire a 55 kilogram cannonball at 34 meters per second at an angle of 25 degrees above the horizontal, then I fire a 20 gram paintball at 34 meters per second at an angle, some angle theta 2 that's more than 45 degrees. And that paintball lands on the cannonball I shot. So what angle is theta 2? Assuming I'm ignoring air resistance. And then which of these, the paintball or the cannonball, took longer to reach its destination? I will tell you, I have given you more information than you need for this particular problem. I'll give you about a minute or so to think about that. If you have a guess, just let me know. Yeah. So, well, here I have two projectiles fired at the same speed that land at the same place. And I know they don't have the same angle. That's why I tell you theta 2 is greater than 45 degrees. The masses aren't important. So the important thing is that because there's two projectiles fired at the same speed that traveled the same horizontal distance, that means their angles are either the same or they're complementary. Well, we know the angles aren't the same because I told you that theta 2 was greater than 45 degrees. So theta 1 plus theta 2 has to equal 90 degrees. These are complementary angles that add up to 90 degrees. So theta 1 is 25 degrees. Theta 2 is going to be 90 degrees minus theta 1. 90 minus 25 is 65 degrees. So I fired the paintball at 65 degrees. And of those two, the paintball and the cannonball, one fired at 25 degrees and one fired up at 65 degrees. Which one do you think took longer to reach its destination? Any guesses?
The one that gets probably.
Yep. It took a longer path and traveled slower. So the paintball has a longer path. It actually also travels slower on average. So it takes a longer time. And that's the end of chapter 2. So we will start up chapter 3. So just some important equations from chapter 2. Average speed is distance over time. Average velocity is displacement over time. If you have an object that's starting at rest with constant acceleration, the distance it travels is 1/2 acceleration times time squared. The relevant version is for a dropped object. The distance traveled by a dropped object is 1/2 gt squared. G, gravity, the acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. Acceleration is change in velocity over time, so final velocity minus initial velocity over time. That can be rewritten as final velocity is initial velocity plus acceleration times time. For circular motion, acceleration, for centripetal acceleration is speed squared over the radius. And relative motion, the velocity of A with respect to C is the velocity of A with respect to B plus the velocity of B with respect to C. So these are the kind of equations you might need on the quiz and the exam. You might also just go through all the slides. So that was chapter 2. And we also have chapter 3, which we will start up on force and motion. And of course, Zoom did the stupid thing. Okay. So we spent chapter 2 basically describing what happens with motion. But we didn't talk about what causes motion. What causes motion is force. That's what we're going to cover here in chapter 3. So we discussed how to describe motion, velocity, acceleration. Those are descriptions of motion. It's called kinematics. We want the technical term. Now we're moving into what's known as dynamics. We're discussing the cause of motion. So in chapter 2, we studied motion, but not its cause. We talked about how we can describe motion, but we didn't talk about what causes it. Here we're going to look at both the cause, force, and the effect, motion. We're going to cover Newton's laws of motion, Newton's 3 laws of motion, Newton's law of universal gravitation. So what we covered with gravity is what happens with gravity near the surface of the Earth, where G is more or less constant. But Newton was able to work out a general version of gravity that explains gravity both on Earth and out in the solar system, in orbits in space. And then we're going to talk about buoyancy and momentum. Now, Sir Isaac Newton was only about 25 when he formulated most of his discoveries in math and physics. And then he waited like a decade or 2 to publish them. And his book, Mathematical Principles of Natural Philosophy, is in many ways considered to be one of the most important publications in the history of physics. He basically started a number of fields of physics, classical mechanics, optics. He invented calculus to make the math for physics easier. And then Leibniz also invented calculus, and then they said nasty things about each other back and forth. Normal sorts of things. So let's start by talking about what force is. Force is a push or a pull. So, I can push on the wall here, applying a force. The wall will push back on me. So a force is a vector quantity. It has a size and a direction. And it's capable of producing motion or a change in motion. So if I apply a force to this mass, I can make it start moving, or I can apply a different force that changes the way it's moving. And then there's a force between the mass and the table, which brings it to a stop. So a force is capable of changing an object's velocity and therefore producing acceleration. Now, you can have a situation where, because of multiple forces acting on an object, they cancel out and there is no change in motion happening. So in fact, here, with this weight sitting on the table, there are at least two forces acting on it right now. Gravity is pulling it down and the table is pushing it up. But the table is pushing up with the exact same force that gravity is pulling down, so it doesn't move. And the units for force are newtons. 1 Newton is 1 kilogram meter per second squared. That is the unit for force. So so 1 Newton is 1 kilogram meter per second squared. So we measure force in newtons. So here we have an example where forces are balancing out and canceling out. The forces are equal in magnitude, equal in size, but in opposite directions, so they cancel out. Much like the force of gravity pulling down on that weight and the force of the table pushing it up. So here we have two forces that are balanced, equal in magnitude, opposite in direction. They cancel out. Right now, all of you are sitting down. The force of gravity is pulling you down. The force of your chair is pushing you up. You are experiencing balanced forces. If you have unbalanced forces, you have some total or net force when you add up the forces. So this has some total net force to the right. Here, this team is applying more force than this team. And so the rope moves to the right in the direction, it accelerates in the direction of the force. So here, if you have a block experiencing a 2 Newton force to the north and a 3 Newton force to the south, what do you think the total or net force on this block is? Now 3 Newtons north, 2 Newtons north and 3 Newtons south, as shown in my little sketch. Well, we have 3 Newtons pulling south, 2 Newtons pulling north. We've got more force pulling south than north, so our net force is going to be in the south direction south. And two of it is going to get canceled out by the 2 Newtons pulling north. So our net force is force 1 plus force 2. You can think of north as positive and south as negative. So 2 Newtons north plus negative 3 Newtons because it's south. The net force is minus 1 Newton or 1 Newton to the south. Here, we have another block. This one has 4 Newtons to the north and 4 Newtons to the south. So what do you think the total force on it is? Yep, they cancel out. That force is force 1 plus force 2, 4 Newtons plus minus 4 Newtons, 0 Newtons. These forces will cancel out. They're balanced. Nothing's going to happen with this block. It's just going to sit there. Now here, we have a two-dimensional problem, but it's reasonably straightforward. We have a block that has 2 Newtons to the north, 3 Newtons to the west, and 3 Newtons to the east. So the forces look something like that. So what do you think the total force on this block is? Yep. The east and west forces cancel out, and all you're left with is the forces to the north. You can write it out like this, but you could think of that the north force is in the y direction and the east and west are in the x. 2 north plus 3 the east plus 3 west. These cancel out, leaving 2 north. And a lot of the time, we'll talk about things where there are just forces that cancel out that we don't think about. Like if you have a car going down the road, the forces you're interested are in the direction of travel. So you're interested in how much the car is being pushed forward and maybe dragged from the air. But there is also forces of gravity pulling the car down and from the road pushing the car up. They cancel out, so we don't worry about it. So Newton's first law of motion was kind of an impressive thing to figure out because it is actually kind of counterintuitive. Because in everyday life, if you take something and you put it in motion, it comes to a stop. So Aristotle, several thousand years ago, considered that the natural state of most things was to be at rest. And then the heavens kept going in circles because their natural state was to be moving, because they were perfect and made of matter. Galileo, by studying the actual motion of objects, realized that theoretically an object could naturally remain in motion indefinitely. And Isaac Newton was able to sort of put this together and write up a description of this. Newton's first law of motion basically is saying what happens if you do nothing. If you leave something alone, if there's no net force on an object. So an object will remain at rest or in uniform motion in a straight line, i.e. traveling at a constant speed in a straight line, unless acted on by some external unbalanced force. So basically, if you leave something alone, it'll keep going in a straight line at whatever velocity it had until a force acts on it. That's Newton's first law of motion. There's not really an equation for that because it's saying what happens when the force is zero. It is a consequence of, it falls out of one of the equations we'll cover when we get to Newton's second law, but Newton's first law basically just says that if, I mean, here I can write it out. It's basically if the net force equals zero, velocity is a constant. So an object will remain at rest or in uniform motion in a straight line unless it's acted on by an external unbalanced force. Balanced forces are ones that cancel out, so of equal magnitude in opposite directions. And an external force is defined as some force applied from outside the object. Turns out internal forces can never change the velocity of a system. They can move the internal bits around, but they can't cause the whole thing on average to change its speed. So here's an example where it's space. The classic example is sort of a spacecraft keeps going because no forces act on it to stop it. And I think what's hilarious about this choice of picture by the textbook is that there are forces accelerating this spacecraft at the moment shown in this image because it is currently in orbit around the moon, being pulled by the moon's gravity. So, yeah, not the best example, but that's sort of the best, closest we can get. here we have an example, this large rock in Yellowstone National Park will stay put unless a force acts on it that's big enough to cause it to move. So this leads to the idea of inertia. So inertia is the natural tendency of an object to remain in a state of rest or in uniform motion in a straight line. This concept was first introduced by Galileo. Basically, objects tend to maintain their state of motion and resist change. And the more massive an object is, the harder it is to change its motion. So Newton went one step further and he related an object's mass to its inertia. The greater the mass of an object, the greater its inertia. The lower the mass of an object, the less its inertia. It is harder to move big, massive things than little light things. Basically, is what it boils down to. So here's an example. The large man will have more inertia than the small child. So it takes more force to get the large van swinging, and it will take more force to bring the large van to a stop. This is partially why when you were a kid, you could do all kinds of dumb things and bounce off of things and fall down and stuff. And as you get older and physically larger, it takes more force to bring you to a stop, so you're more likely to injure yourself. There's other factors there, but it is one factor. And you may have seen this trick where you have some massive object. Let's see if I can do a quick example here, like this mass or a roll of quarters, or traditionally a fully set table on a tablecloth. And if you pull out the thing underneath the massive object fast enough, the inertia of the object keeps it in place. So the trick with the tablecloth is by removing it very quickly, the inertia of all the objects keeps them in place, and they don't move, nothing falls over. You've just performed a dramatic magic trick. If you do it slowly, there's enough time for the forces to apply, and the objects will fall over and you make a mess. So because of this relationship between motion and inertia, Newton's first law of motion is sometimes called the law of inertia. And a lot of other things that we use that are safety devices exist to basically help correct for the fact that we have inertia and would like to keep moving under sudden changes in speed. So seatbelts, for example, if you didn't have a seatbelt, your inertia would cause you to keep traveling forward when your car comes to a sudden stop because you, I don't know, ran into a tree. And that would not be good because then you would come to a sudden stop when you run into the hard things in your car, like your windshield or your steering wheel. And so another thing is that often a lot of safety devices are designed to cause your change of inertia to take longer period of time than it would if you slammed into something. They slow down the process of you slowing down, and that helps prevent injury. So here is an example. If you have a motionless mass held up against gravity by a string, if the tension of the string is providing an upwards force of 10 newtons, how much force is gravity pulling the mass down? So this is basically, I have a mass hanging from a string. I know this string is pulling up with 10 newtons of force. So how much is gravity pulling the mass down? Yep. So we have 10 newtons up, some amount down. The total has to be 0 because the object isn't moving. That was actually a pretty good demonstration that gravity pulls down on a 1 kilogram mass with about 10 newtons of force. So the tension plus G, 10 newtons of force in tension, plus the force of gravity. Force of gravity is going to be minus 10 newtons down. And if you've ever used a spring-based scale, like one of those scales that you hang a weight on it, I don't know, they used for weighing like vegetables in grocery stores and stuff. That's what that's measuring. It's basically measuring the tension, how hard it's pulling up to counteract gravity. Now, a scale you stand on is actually measuring how much it's pushing up to counteract your weight. And that's generally how scales work. They measure the force required to counteract the force of gravity on you. So here we have a rocket starting from rest in deep space. It has an acceleration of 144 meters per second squared for 20 seconds, and then it uses up all its fuel. Then after it's used up all its fuel, it doesn't have any force anymore. So 3 hours later, what will its speed be? I'll let you think about this for a little while. Nope. That would be its speed after 1 second. Yep. So what happens is that for 20 seconds, it accelerates at 144 meters per second squared. So at the end of that final 20 seconds, we can use this formula from chapter 2. Final velocity is initial velocity plus acceleration times time. We started at rest, so initial velocity is 0. Acceleration is 144 meters per second. Time is 20 seconds. So our final velocity after 20 seconds is 2,880 meters per second. At which point, the force stops. So there's no force. No force means velocity remains constant. We all have a continuous constant velocity of 2,880 meters per second after 3 hours. Nothing's going to change once it runs out of fuel and the force stops, basically. So there, while it has fuel, it has an unbalanced force causing this acceleration. And then once the fuel runs out, it doesn't have any force anymore, so it just coasts at a constant velocity. Here's a little more straightforward of a question. The first law questions are always a little awkward. So here, a frictionless block slides down a 3-meter hill, achieving a speed of 29.4 meters per second when it reaches flat ground. Along the flat ground, how long does it take to travel a distance of 441 meters? So this is a similar situation. Once it hits the flat ground, it will travel at constant speed. At constant speed of 29.4 meters per second, it's traveling a distance of 441 meters. Distance equals speed times time. The time is distance over speed. 441 meters over 29.4 meters per second is 15 seconds. Oops, sorry. Now here, if I have a block that's spinning clockwise on a 1-meter string at 19.7 meters per second, and it is released when the string is pointing east. So how fast and in what direction does the block travel after that? Assume there's no other forces acting on it once it's released. That's the speed. No, it will be south. So here, when the string is pointing east, it's going clockwise around the circle, so the block is traveling south. And when the string is removed, it just keeps flying at 19.7 meters per second. So its speed is 19.7 meters per second south. So if you're spinning something around to throw it, you don't throw it when the string is pointing in the direction you want it to go. You throw it when it's moving in the direction. So if you're doing like an overhead slingshot, you throw it when the sling is pointing towards your target, the thing you release will slam into the ground and look and feel silly. Now, we talked about what that acceleration leads, that force leads to an acceleration. Newton's second law of motion describes this. It says that the acceleration, a change in velocity caused by a force, is proportional to the force applied, directly proportional to the force applied. If you push harder, you get a bigger acceleration. And it is inversely proportional to the mass of the object. The more massive the object is, the less acceleration you get for the same force. So the greater the force, the greater the acceleration. The greater the mass, the smaller the acceleration. And Newton's second law is that acceleration is force over mass. Or, as it is more commonly written, force is mass times acceleration. And we define our units such that force equals mass times acceleration. We don't need any conversion back. That's how a Newton is defined. A Newton is the force that, when applied to a mass of 1 kilogram, causes an acceleration of 1 meter per second squared. So the bigger the force, the bigger the acceleration, the bigger the mass, the smaller the acceleration. And this actually also covers Newton's first law. Because if force, because this force here is the net force, the total force. If the net force is 0, the acceleration is 0. So the velocity doesn't change. So here's some examples. For a given force and a given mass, you'll have an acceleration of a. If you double the force, you'll have twice the acceleration. If you double the mass but keep the original force, you'll have half the acceleration. So force is the net force, the total force, which is likely the sum of 2 or more forces. Mass and acceleration are concerning the whole system. The units are mass times acceleration, so kilograms times meters per second squared, which we call newtons because no one wants to write out kilogram meters per second squared all the time. And this is a derived unit, and it's the metric system's unit of force. The US customary unit of force is the pound. There's also a mass pound. And, the more I find out about US customary units, the more of a horrible historical mess they are. And then you find out that everything is slightly different in the way that they're used in English for things. And it kind of just makes you want to scream. So here's an example of net force and total mass. So here we have 2 forces. We have plus 8 newtons pulling over here, minus 5 newtons pulling over here, and 2 masses of 1 kilogram, but the whole thing can be treated as a system. So what's the acceleration of this system? Well, the total force is 8 newtons plus negative 5 newtons, or plus 3 newtons. and the total mass is 2 kilograms. So, 8 newtons minus 5 newtons over 1 kilogram plus 1 kilogram. The acceleration is 1.5 meters per second squared. And I think actually this is a decent place to stop for today. So I'm going to stop here for today. And I'll see you guys next week. Your quizzes are graded, the grades are up, but there's a couple people who need to take it. But if you want it, I can give you your quiz. I'll let the people who need to make up the quiz make the quiz up right now.